Okay, here's sample problem 5.5. A metal pellet with a mass of 100.0 grams originally at 88.4 degrees Celsius is dropped into 125 grams of water originally at 25.1 degrees Celsius. The final temperature of both the pellet and the water is 31.3 degrees Celsius. Calculate the heat capacity C in joules per degree C of the pellet. Okay? So here's essentially what we're doing. We're taking a metal pellet and we're going to dunk it into a sample of water. Okay? And in this particular problem, they give us the mass of the pellet. And they tell us that it's initially at 88.4 degrees C. And then it gets dropped into water, which weighs 125 grams. And the water is at 25.1 degrees C initially. And then after you drop the pellet in, look what happens. The pellet, its temperature goes down to 31.3 degrees C. And the temperature of the water goes up to 31.3 degrees C, right? And that's what you would expect to happen. You would expect the water to get warmer. If you drop something hot into water, the water is going to warm up. And if you drop something hot into water, whatever you dropped in is going to get colder. And so they'll eventually reach the same temperature, right? That's called, by the way, thermal equilibrium. You can impress people with your terminology. Oh, thermal equilibrium. They're at the same temperature. That's all that means. Okay, so how do we go about doing this? Well, you have to be very careful about it. What's happening is, remember, when you're talking about heat transfer, the direction is important. Heat transfers from the hotter object to the colder object. So if this one's hot and this one's cold, the heat's going to go this way. Right? And that's what's happening here. The pellet is transferring heat to the water, so the water gets hotter. Okay? So what I'm going to do is I'm going to say the following. We cannot create energy. Get it out of your mind that you can create energy. You are not able to create energy. So what we're going to do is we're going to say that no matter what happens, the change in energy has got to be zero because we cannot create nor can we destroy energy. So whatever we're going to do, it's going to add up to zero. So here's how I'm going to do it. The amount of heat that gets transferred to the water plus the amount of heat that's transferred from the pellet has got to be zero. Okay? Law of conservation of energy. So now the question then is, well, how do you solve for Q? Well, we have calorimetry equations. We know the mass of the water. We can look up the specific heat of water. So what I'm going to do is I'm going to write this QW as S of water, oops, not plus, times the mass of the water times the change in the temperature of the water, right? That's our calorimetry equation. But remember, we had two calorimetry equations. The other one, for the pellet, I'm going to use this one. Cp dt, delta T. Okay? Why am I using C as opposed to S? Go back to the question. Calculate the heat capacity C of the pellet. So that makes sense, right? The heat capacity is what it asks us to find. So let's just go ahead and use that form of the calorimetry equation. We could do Sm delta T, but they want the heat capacity. If they had said, hey, it weighs 100 grams and we want the specific heat of the metal, we could do that. We could do Sm delta T, but it asks for C. Those two added together are zero, right? Now we want to know the heat capacity. So here's what I'm going to do. I'm going to subtract the heat term for water from both sides. So I'm going to subtract Sm delta T for water from both sides. And when we do that, we'll have C of the pellet times delta T equals minus Sm delta T, right? I just subtracted it from both sides. So it disappears on the left side and appears as a negative on the right. Last step, divide both sides by delta T. So minus, sometimes it's useful, it's sort of a form. You don't have to do it this way. I'm going to write the negative in front of this ratio. Oops, running out of energy here. Oops, I forgot to put that this is delta T of the pellet. So S, W, M, W, delta T, W. Now it's just a matter of putting the numbers in, okay? So let me move it over here just so that I've got enough space. So minus specific heat of water, 4.184 joules per gram degree C. Mass of the water, 125 grams, right? Change in temperature of the water. Okay, let me go ahead and calculate that. We started at 25.1, we ended at 31.3. So for the water, 31.3 minus 25.1 is 6.2. And now let's do it for the metal. For the metal, it started at 88.4 and ended at 31.3. So that would be 31.3 minus 88.4, which is negative 57.1. So notice we have a negative divided by a negative. Well, that's going to give you a positive, right? We should end up with a positive value for specific heat. So the sign looks good. So 4.184 times 125 times 6.2 divided by 57.1. The negatives are gone, and we get 56.8. And let's make sure we get the units. It's degrees C here, degrees C there. So then we have grams here and grams there. So joules divided by degrees C. And yeah, they tell you, look, they tell you it's going to be in joules per degree C, and that's what the units work out. So that's the heat capacity. And the interpretation of that is that if you put in 56.8 joules of heat into that pellet, it will increase its temperature by 1 degree C. It'll go from 20 to 21 or 53 to 54. Or if you take out 56.8 joules of heat, it will go from 88.4 to 87.4 or 32.3 to 31.3. Okay, that's called the heat capacity, and there you go.